Okay, so this week you sent in some really fascinating material,
Yeah,
and we're going to do a deep dive into it, and I'm super excited about it. It's
absolutely.
all about group homomorphisms and normal subgroups.
Right.
And we're drawing from a couple sources.
hmm
Um, the Contemporary Abstract Algebra textbook,
Okay.
and then also some like FAQs and study guides.
Yeah.
So a lot of really, really good stuff that's going to help us really understand these concepts.
Right.
Um, and you might be thinking abstract algebra,
Yeah.
when am I ever going to use this?
Right.
But honestly, like understanding these structures,
hmm
it's like getting a secret decoder ring for mathematical thinking.
Yeah.
It really is. And it reveals some incredibly powerful ways to spot patterns,
Right.
not just in, advanced math,
Mm.
but in all sorts of systems.
That's right.
And that's why it's so cool.
Yeah.
So our mission today is to try to unpack this crucial link between group homomorphisms and normal subgroups
Absolutely.
and see why they are such cornerstones of abstract algebra.
Yeah. And what's fascinating is that
Right.
they provide this framework for understanding
Yeah,
the relationships between different algebraic structures.
that's right.
So it's a lens that sharpens your intuition
Yeah.
for mathematical connections.
So let's dive in with group homomorphisms.
Okay.
So the definition that we have from contemporary abstract algebra describes a function.
Okay.
Let's call it phi,
Mm-hmm.
between two groups, G and G bar.
Okay.
And this function respects the group operation.
Right.
So simply put, phi of AB equals phi of a times phi of B.
Exactly.
And this is key. The operation AB on the left happens in group G.
That's right.
And the operation phi of a times phi of B on the right happens in group G bar.
Okay.
So this was pointed out in the FAQ.
Mm.
And I thought that was really important because,
Yeah.
you have to remember that those operations,
Right.
they're happening within their own group.
Yeah, it's translating the
Yeah.
structure from one group to
Yeah,
another.
exactly. And
Yeah.
so,
And preserving that form of the group operation.
like contemporary abstract algebra notes,
Yeah.
the term comes from the Greek roots meaning like form.
Mm-hmm.
So it's like a natural step up from an isomorphism
Kind of right.
where the forms are not just alike, but essentially identical.
Yeah.
And so the study guide also gives us some related terms
Mm-hmm.
that build on this.
Okay.
So we have isomorphisms,
Right.
which are homomorphisms that are also bijective.
Okay.
So that means they're one-to-one and onto.
Yeah.
So isomorphisms tell us when two groups are structurally the same.
Mm-hmm.
Then we also have monomorphisms,
Right.
which are just one-to-one homomorphisms.
Okay.
And epimorphisms,
Yes.
which are onto homomorphisms.
Mm-hmm.
And then finally we have automorphisms,
Right.
which are isomorphisms from a group to itself.
Okay.
So all of those are kind of,
Have they let us be
more precise
yeah.
in how we describe these relationships between groups.
So an isomorphism is a perfect structural match,
Right.
whereas the others
Yeah.
really highlight different aspects of
Yeah.
how one group can be embedded within
Okay.
or mapped onto another
Right.
while still respecting that fundamental operation.
Okay, cool. So we've got, the homomorphism,
Yeah.
the different types of homomorphism.
Right.
Now let's talk about the kernel.
Okay.
So the FAQ defines the kernel of a homomorphism.
Mm-hmm.
And so we have phi mapping from G to G bar.
Right.
And it defines the kernel as the set of all elements, X and G,
Mm-hmm.
that get mapped to the identity element,
Okay.
E bar and G bar.
Okay.
And so in symbols, this would look like the kernel of phi equals the set of all X and G, such that phi of X equals E bar.
Right.
So it might seem simple,
Mm-hmm.
but it's really profoundly important.
Yeah, it's fascinating
Yeah.
because the kernel, like both of our sources stress, is
Mhm.
always a subgroup of
Yeah.
the original group G.
Exactly.
And the quiz answer from the study guide briefly explains why this is. It
Right.
contains the identity of G
Right, because phi of E
because 5e maps
equals E bar.
to E bar, right?
Okay.
And it's closed under the group operation, and it's closed under taking inverses.
Right.
So it has this nice, well-behaved algebraic structure.
Yeah, so the kernel itself is a group.
Yes.
And Chapter 10 of Contemporary Abstract Algebra
Okay.
gives us a lot of examples to really help solidify this.
Okay.
So, we see that the kernel of any isomorphism is just the trivial subgroup, the set containing E,
Right.
which contains only the identity.
Only the identity can map
And that makes perfect sense.
to the identity.
Because if it's one-to-one,
Exactly.
only the identity can map to the identity.
Right. If the mapping is injective,
Yeah.
no other element can land on the identity in the codomain.
Okay, cool. So then we get some more,
Yeah.
concrete examples. So like the kernel of the determinant mapping from GL to R, the group of invertible 2x2 real matrices under multiplication, to R star, the group of non-zero real numbers under multiplication,
Right.
is SL2R.
Oh.
The set of 2x2 real matrices with a determinant of 1. So that's like a really neat link between...
Yes, it demonstrates how that specific property, like the determinant being 1, defines a significant subgroup that's inherently connected to a homomorphism.
Okay, cool. And then we also see the kernel of the mapping phi of X equals the absolute value of X.
Okay.
From R star under multiplication to the positive reals under multiplication is the set containing 1 and negative 1.
Okay.
Because both 1 and negative 1 have an absolute value of 1.
Right.
Which is the identity.
Which is the identity.
In the positive reals.
In the positive reals under multiplication.
Under multiplication, yeah.
Yeah.
Okay, and then another one looking at polynomials.
Okay.
The kernel of the derivative mapping.
Yeah.
From Rx, the polynomials with real coefficients under addition to itself is the set of constant polynomials.
Okay.
Since their derivative is 0.
Right.
Which is the identity in Rx under addition.
Right. Yeah, these examples really illustrate how the kernel acts like a filter.
Yeah.
Capturing those elements that are nullified or mapped back to the identity under the homomorphism.
Right.
Providing crucial insights into its behavior.
Okay, so we've got, the kernel of the derivative mapping.
Yeah.
And then we have the kernel of the mapping phi from Z to Zn.
Okay.
Defined by phi of m equals m mod n.
Right.
Is nz.
Okay.
All the integer multiples of n. And this makes perfect sense.
Right.
As these are exactly the numbers that are congruent to 0 mod n.
Right.
And 0 is the identity in Zn under addition.
That's right.
So we're really seeing like...
Yeah. And it even continues into more abstract settings.
Yes, exactly.
Like you have the Gaussian integers Z, the units U40, and symmetric groups.
Yeah.
With their respective kernels, showcasing diverse structures.
Absolutely.
So like the kernel of the sign of a permutation mapping from EPSN to Z2 is the alternating group.
Right.
And consisting of all the even permutations.
Right.
So it really highlights the broad applicability of this concept.
It does. And that it's not just...
Yeah, and the kernel isn't just a technicality.
Yeah.
It corresponds to a naturally occurring and important subgroup within the domain.
Okay. So we've got homomorphisms.
Yeah.
We've got their kernels, which are always subgroups.
Right.
Now we need to introduce normal subgroups.
Okay.
And Chapter 9 of Contemporary Abstract Algebra defines a subgroup N of a group G as normal. If for every element G in G and every element N in N, the element inverse is also an N.
Okay.
And this is equivalent to saying that the left coset Gn is the same as the right coset N for all G and G.
Right. That condition inverse being an N is really fundamental.
Yeah.
Because it means if you take an element from the normal subgroup N, act on it with an element G from the larger group G by conjugating it with G, the result will always stay within N. So it's this invariance under conjugation that gives normal subgroups these special properties.
Okay, so just like with kernels, the book gives us some important examples.
Right.
So for instance, it points out that every subgroup of an abelian group is normal.
Okay.
And this makes sense because if G is abelian, then Gn equals N.
Right.
So G inverse equals N inverse, which equals N.
Right.
Which is clearly in N.
So commutativity really simplifies things when it comes to normality.
Okay, and we also learn that the center of any group G, which is the set of elements that commute with every element in G, is always a normal subgroup.
Okay.
So again, if Z is in the center of G, then for any G in G, G inverse equals G inverse G, which equals Z, which is back in the center.
So the center is like the most commutative part of the group. So its normality is a logical consequence of that.
Okay, so we've got, those two examples, and then we have other examples like N being normal in Sn, SLNR being normal in GLNR.
Okay.
And the set containing E in R180 being a normal subgroup of the dihedral group of order 8.
Yeah, so these examples start to illustrate normality in non-abelian groups.
Right, where
doesn't always equal N.
Doesn't always equal N,
Yeah,
right?
yeah.
They demonstrate that normality isn't just a trivial condition.
Right.
It often arises in crucial structural relationships between subgroups and their parent groups, even when the parent group isn't commutative.
Okay. The book also mentions that if H is a subgroup and K is a normal subgroup of G, then HK, the set of all products, HK where H and K is in K, is also a subgroup of G.
Okay.
So this shows how normal subgroups interact predictably. That's right, and that's a useful property.
Yeah.
That streamlines working with subgroups.
Okay.
The normality of K ensures that the product HK maintains the necessary closure and inverse properties to form a subgroup.
Okay, cool. We also get a glimpse into the normal subgroups of A4 and D4.
Okay.
Highlighting, specific subgroups that satisfy the normality condition.
Right.
And then there's the introduction of the normalizer, NH of a subgroup H, which is the set of all elements G in G, such that GHG inverse equals H.
Okay.
And so clearly H is normal in G.
Right.
If and only if its normalizer is equal to G.
So the normalizer provides a measure of how close a subgroup is to being normal.
Okay.
So if the normalizer encompasses the entire group, then that subgroup is indeed normal.
Okay, so we have homomorphisms. We have kernels, which are always subgroups. We have normal subgroups. Now for the pivotal connection, the kernel of any homomorphism is always a normal subgroup.
Yes, that's a fundamental result.
Yeah.
Linking these two concepts inextricably.
And we've seen that kernels are subgroups.
Right.
And the definition of the kernel directly leads to the normality condition.
Yeah, every homomorphism you encounter automatically brings with it a normal subgroup.
Yeah.
Its kernel.
Okay, so the kernel of any homomorphism is a normal subgroup. But the relationship goes even deeper.
Yes.
Every normal subgroup, N of G, is the kernel of some homomorphism.
That's right.
And specifically, it's the kernel of the canonical or natural homomorphism, gamma, mapping from G to G mod N.
Okay.
Defined by gamma of G equals Gn.
Right.
So that's G times the coset N.
That's a G times the coset N,
And indeed, the kernel of this map is exactly N.
Right.
Because Gn is the identity element in G mod N, which is the coset N itself.
Right.
If and only if G is an element of N.
Yeah, this converse is equally vital. It tells us that normal subgroups aren't just arbitrary subgroups.
Yeah.
They arise naturally and universally as the things that get mapped to the identity element under homomorphisms. So it's this bidirectional relationship that is quite profound.
Absolutely.
Okay.
So this naturally leads us to factor groups or quotient groups.
Okay.
So if N is a normal subgroup of G, we can construct a new group, G mod N, whose elements are the cosets of N in G.
Right.
And the operation in this new group is defined as N times Bn equals ABN.
Oh, okay.
And FAQ number 6 emphasizes that the normality of N is absolutely crucial.
It's crucial.
For this operation to be well-defined.
It acts as the guarantor that the quotient structure is coherent and forms a well-behaved group in its own right, independent of the choice of coset representative.
Okay, and then the order of a finite factor group, G mod N, is simply the order of G divided by the order of N. So the order of G mod N equals the order of G divided by the order of N.
And this provides a powerful tool for determining the size of these newly formed factor groups.
Yeah, it's a direct consequence of Lagrange's theorem.
Right.
Given that all cosets have the same size as N.
Yeah, it connects the order of the quotient group back to the orders of the original group and the normal subgroup.
Okay, so now we've built up to like a real powerhouse.
Yeah.
The first isomorphism theorem, also known as the fundamental theorem of group homomorphisms.
Right. This theorem is truly fundamental.
Yes. And the study guide states it clearly. If phi mapping from G to G bar is a homomorphism with kernel K, then the factor group G mod K is isomorphic to the image of phi, denoted as phi of G.
Yeah, it ties together all the pieces we've been discussing.
Yes.
Essentially, it tells you that by understanding what gets squashed to the identity by the homomorphism, the kernel K, you can perfectly understand the structure of what remains after the transformation.
Right.
The image phi of G.
Yeah, and they So what here is huge.
Yeah.
This theorem gives us a really powerful tool for understanding the structure of homomorphisms.
Right.
So the kernel K represents the elements that are essentially lost in the mapping.
Yeah.
And when we form the factor group G mod K, we're saying, let's consider elements that differ by something in the kernel as being equivalent.
Okay.
And what remains is a group that has the exact same structure as the reachable part of the codomain phi of G.
Right. It provides a kind of accounting principle for the structure of G under the mapping phi.
Yeah.
So some of the structure collapses into the identity, the kernel.
Yeah.
And the rest is faithfully preserved in the image phi of G.
Exactly.
With the first isomorphism theorem providing that relationship between the two.
Right.
Via the quotient G mod K.
Okay. And FAQ number 8.
Yeah.
Rightly emphasizes the theorem's importance in understanding the relationships between groups, normal subgroups, and homomorphic images.
Right. It acts as a central hub connecting these concepts.
Yeah, it really is a cornerstone for proving other crucial results.
Yes. You often use the first isomorphism theorem to establish that certain factor groups are isomorphic to other, perhaps more familiar groups.
Yeah.
Which can significantly illuminate their internal structure.
Absolutely. Okay, so the study guide also outlines some key properties that are preserved by homomorphisms.
Right.
Yeah. And so we've already noted that the identity maps to the identity and inverses map to inverses.
Yes.
But it also states that the homomorphic image of a subgroup is itself a subgroup.
Right. These preservation properties are essential for understanding how homomorphisms interact with the subgroup structure of the groups involved.
Yeah.
They ensure a degree of predictability
Right.
in how subgroups are transformed under the mapping.
Okay. We also learned that if the original group G is cyclic,
Right.
meaning it can be generated by a single element,
Okay.
then its homomorphic image phi of G will also be cyclic.
Right, because these properties are preserved
Yeah.
by the structure-preserving nature of the homomorphism.
Exactly.
Right.
And similarly, if G is abelian, meaning its operation is commutative, then phi of G will also be abelian.
Right.
And finally, we see that if an element A in G has a finite order,
Okay.
say the order of A equals n,
Yeah.
then the order of its image phi of A in G bar must divide n.
Yes. This provides a constraint on the possible orders of elements in the homomorphic image, which can be valuable when you're analyzing homomorphisms between specific groups with elements of known orders.
Okay, and then our study guide also includes a brief mention of Cayley's theorem,
Okay.
which states that every group G is isomorphic to a subgroup of the symmetric group on G.
Yeah.
And, while it's slightly outside the direct connection between homomorphisms and normal subgroups, it's a really profound result.
It is.
Demonstrating that every abstract group can be represented concretely as a group of permutations of its own elements.
It's a foundational theorem
Yeah.
that provides a way to visualize and work with abstract groups by embedding them within this well-understood framework of permutation groups.
Okay, so to kind of bring it all together, we've taken this deep dive into the intricate relationships between these concepts.
Absolutely.
We began by defining group homomorphisms as mappings that preserve the group operation.
Okay.
We then explored the kernel of a homomorphism, which we discovered is always a normal subgroup of the domain group.
Right.
Conversely, we learned that every normal subgroup arises as the kernel of some homomorphism, leading us to the construction of factor groups.
Right.
And finally, the first isomorphism theorem beautifully and powerfully links these ideas.
That's right.
Revealing that a group modulo, its kernel, is structurally identical to the image of the homomorphism.
And placing this within a broader context, understanding these concepts goes beyond the manipulation of abstract symbols. It cultivates a deeper appreciation for how algebraic structures relate to each other and how new structures can be derived from existing ones.
Exactly.
And the underlying principle of preserving structure under a mapping is a recurring and fundamental theme throughout mathematics.
Absolutely. And even if you know abstract algebra isn't a subject you'll directly teach, this exploration into homomorphisms and normal subgroups sharpens your ability to recognize underlying structures and their transformations.
Right.
And that skill is incredibly valuable across various fields of mathematics and beyond.
Absolutely.
So this prompts a thought
that
I have for you to consider. Where else in mathematics,
Mm.
or even in the world around you? Do you see examples of structure-preserving maps?
Right.
Where might you find things that are like other things in their fundamental organization?
Yeah, reflecting on those likenesses
Yeah.
can often lead to surprising connections and a deeper understanding of the principles at play.
Absolutely. So hopefully this deep dive has illuminated these fundamental concepts for you. Abstract algebra holds a universe of fascinating ideas.
It does.
And, understanding homomorphisms and normal subgroups is a crucial step in that exploration.
Absolutely.
So thanks for joining us on this dive.
Yeah, thanks for having me.
Absolutely.